Welcome back. In the last couple of lectures, we looked at trees, their properties, and ways of traversing the trees. And today, we are going to look at implementing priority queue operations using trees. Okay, and I recall what are priority queue operations. These are, insert and delete max. Right? Essentially, it's like a queue. New objects are coming, but with priorities, some numbers associated with each object. And at any point of time, we want to delete the maximum priority element and service it to a CPU or to a printer or something. Okay. So what we saw was that if you can, if you really want to insert and find max, not just delete max, but just find max, can be done in constant time. Recall the solution was just keep it in an unsorted array and keep track of the maximum. When a new element comes, add it to the end and just compare it with the maximum. If the new element is bigger, update the maximum, otherwise don't do anything. If the maximum is being asked for, give the value pointed to by the maximum value. Okay, I had a question in that slide whether can we do it with constant space. I don't know how many of you thought about this. The answer is yes. We don't even need to store the entire array. We just store only the max value. When the new element comes, update the max. If that is bigger than the max, keep that new element. Otherwise, just discard it. And that is also a good enough solution with constant time and constant space. Okay. Now today, what we want to look at is if I also want to do delete max. Delete max. That solution of just keeping track of the max does not work if we also want to delete the maximum, because once you delete it, you need to know who the next max is, and that requires a linear scan in the list to find, if you store the entire elements, and to find the next max. And we contemplated keeping first and second max, third max, and they were all had problems. Maintain keep sorted array. It has an insertion problem. Sorted linked list has other problems. You can't even insert, because you need to figure out where to insert in a sorted array, and that requires some indexing and so on. So sorted linked list doesn't work. Sorted array has the problem of moving elements. So all that had problems, to achieve logarithmic time. Today, we are going to look at how to achieve logarithmic time for insert and delete max using what are called trees, some special trees, complete binary trees. And recall that this is a binary tree where you open a new level only after one level is full, and such a binary tree we argued has height at most log of n plus 1, and that's going to be very useful for implementing insert and delete max. Okay, so how are we going to do it? Well, the data structure problem is clear. You want to maintain a set of numbers and support insert and delete max. The solution now is I have to tell you how I am going to organize. I'm going to use trees, and then I'm going to tell you how to implement insert and delete max operations, so that the overall worst case time for each of these operations is log of the input size, or order log of the input size. Okay. So the way we're going to do it is store the elements in a complete binary tree. this is one part of the solution. That's one. Also, in a way that elements from a root to a leaf are in sorted order. In decreasing order. More precisely, if elements even repeat, then a better way to say is non-increasing order. What that means is that, first I am going to store it in a complete binary tree, right? Remember, complete binary tree looks like this, something like this. And then I also want to make sure that as you read the elements from root to a leaf, these elements are all in non-increasing order. We will see an example. So, how I am going to set it up is a pre-processing step about which we have not been worrying about. Remember, because when I said sorted array, how do you sort it? Well, that's a one-time thing. We will get to it later. Similarly, this is a setup cost of maintaining it. So, I will give you an example of a set of elements I am going to store like this. So, as I read from root to leaf, elements should be in non-increasing order. That means, if all elements are distinct, that's in decreasing order. Okay. So, for example, I might store 15 here, 7 here, 4 here, 6 here, 3, maybe 3 here, 6 and 2, 12, 11, 9 and maybe 9. So, as you read from root to a leaf, the elements are in decreasing order, or at least non-increasing order. 15, 7, 6, 6, 15, 7, 6, 2, 15, 12, 11, 9, 15, 12, 9 and so on. In particular, how I am going to achieve is that value at the parent is greater than or equal to value at its children. Okay, so this is a property which we ensure. So now I have told you, so this whole thing has a name which is called a heap. So I am storing the elements. Okay, you want me to maintain a bunch of numbers, remember, to support insert and delete max. So I am going to store maintain this number in a complete binary tree. First of all, put every node is going to have one of those values which I want to store, and with the additional property that the value at its of any parent is greater than or equal to value at its children. So 15 is greater than or equal to 7 and 12, 12 is greater than or equal to 11 and 9, 11 is greater than or equal to 9, 6 is greater than or equal to 6 and 2 and so on and so forth. Okay, so this whole arrangement is called a heap. Complete binary tree notes at the values at the nodes with satisfying value of a parent is greater than or equal to value of children. That's it. That's my solution. Okay. How am I going to organize my data? Here it is. This is the way I am going to organize. Now, to complete the solution for the data structure problem, I have to tell you how to insert and how to delete the maximum element. Okay, and I want to argue that the both can be done in order log n time. Now, one good thing about complete binary tree we saw in the last lecture or the lecture before is that the height of such a tree, if I had height of a complete binary tree, let's on n nodes, is at most log of n plus 1. This is something we proved last time, and that is what I am going to take advantage of. Okay. So, it is a nice bushy tree because I am So, now I am going to tell you how to do my insertion and delete max operation. Okay. So, let us keep this picture in mind. Suppose I want to do insert some new element, let us say 25, right, in this tree. Well, remember, it is a complete binary tree and nodes are filled up in level by level. So, if I have to insert 25, it has to, I have to create these new locations and put 25 there. Okay, it satisfies this property that my values are stored in a complete binary tree, but it may violate this condition. Okay. Well, can it violate arbitrarily? No, only violation it can be with is with the parent of the newly inserted element. So, I compare that element with its parent and I find that yes, there is a violation, then what do? I swap. So, that means 11 comes here and 25 goes here. Can there be a violation? Yes, there can be a violation with this node and its parent, which I compare, and so 25 goes here and 12 goes here. Can there be a violation? Yes, compare with the parent and I go 25 goes here and 15 here. After doing that swap, there won't be a problem, is something you should keep in mind, because so, for example, when I moved 25 up there and I brought 12, what I brought is something smaller than what it was. So, you will have no problem with parent being greater than or equal to its children, because the root to leaf, the whole path is in decreasing order. Okay. So, think of it as I am adding this new element and trying to insert it in this root to leaf path, the last path, the rightmost path. Okay. So, the whole algorithm would be any element for that matter, 25, insert at the rightmost location and while value of the parent is less than value of the node, swap the two values. Now, the new node is the parent. So, then now I compare again. So, I have written very informally, you can translate it into any programming language. So, all I am saying is I will add it at the end, compare it with the parent. If there is a violation, swap, and now I am sitting at this is my new node, compare it with its parent now, because it is a while loop, right, and if there is no violation, done, we can stop. If there is a violation, keep going, swapping, and you will stop when you reach the parent node, when there is no parent at all, because it is a root node, right, or parent does not exist, which means you have reached the root. So, there is nothing, keep doing this. That is all the insert algorithm is, and you can verify that it is correct. It just fixes, it finally, after inserting this new element, it continues to be a complete binary tree, and the parent child relationship is maintained, but the value of a parent is greater than or equal to value of a children is maintained throughout the entire tree. And how much time have we spent? The number of comparisons and swaps you will do is proportional to essentially height of the tree, because you start from a node parent, 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 you're just going up, and so time would be order height of the tree, and since we already know that it's a complete binary tree, it's order log n. So, we have a nice clean algorithm to insert a new element in log n time by maintaining this complete binary tree. Okay. This was not possible in a sorted array or a sorted linked list, but now you can do it. Now, let us look at the other operation we have to perform, delete max, because you have, right, it does not tell you. So, it just says give me the largest element. Thankfully, observation is that max is at the root. Because we ensured this order that parent greater than or equal to its children relationship for every node. So, the root has to be the maximum. So, it's there and I need to delete it. So, let us think about how I am going to do that. Once I delete this node, the total number of values decreases by 1. So, I will do something very natural, take the last element and put it there. Okay, so let me draw the whole tree again and or maybe do some other example. Okay, so let us say I have this tree. Okay, so suppose this is a complete binary tree. Now, the user says delete max. So, that means this element which is at the root is deleted. Somebody has to go fill it up. So, I take the last element and put it there. That way, the structure of complete binary tree is maintained, because I know that it is level by level, it's all nice and complete, but the parent child relationship may be violated. So, I will check where can that be a violation. It's at this point at the root, because that's the only node which changed. So, there is a violation, one is smaller than 7, one is smaller than 15. So, what do I have to? I have to do some swap. Which one do I swap? I have an option of putting 7 up there and 1 here, but then 7 would be smaller than 15, which is so there will be a violation here as well as a violation here. So, it turns out the better thing to do is to pick the larger of the two children, okay, and swap it with the parent. Okay. So, delete root, and I replace it, meaning root value, the value of the last node. Now, again another while loop. If there is no violation, you are done. While parent of value at parent at the root, or which is less than value of some child, replace root value with the larger child value. So, in this case 15, okay, so maybe use a different color. So, 15 will come here and 1 will come here. Now, there may be a violation again here, because whatever the new element has come, that only there can be a violation. By picking the larger element, please verify that this side we have no problem at all. So now we just need to go and check the violation of this subtree. So I will, there is a while loop here. So now root will be the larger child, right. So this is the root, because we are talking about a new tree. So now I check value of the root is less than value of its, right. We just go back here, value of the root is less than value at some child, then yes, I will pick the larger one. So 1 will come here and 10. This is a larger child. Things settle down now. That's it. That's all the delete max operation is. You can verify that it's nice and clean, and the time again would be order log n, because it's proportional to the height of the tree. Unlike insert, now you have to do two comparisons, because you pick the large, compare the children and then compare it with the parent. So there will be like two comparisons at every level, but the number of levels is at most log of n plus 1. So it's order log n. Very nice. Okay. By just using complete binary tree. So we went from an array or a linked list and went on to this little involved complete binary tree. We can perform insert and delete max both in logarithmic time. Very clean solution, nice. Okay. The only thing you need to do is, apart from maintaining a complete binary tree, we also maintain that the value of a parent is greater than or equal to value of its children. This is actually also called max heap, because I am keeping the max at the root. There is also an equivalent min heap, where you ensure that the value of the parent is less than or equal to value of its children, so that the parent will have the min. And there are applications where you want to use min heap, for example, in Dijkstra shortest paths algorithm or something, where you need to keep doing delete min, not delete max. Okay, so that's it. As a data structure point of view, as a solution, we have this clean complete binary tree with the parent child relationship ensures that you can do both insert and delete max in logarithmic time. I am going to make a bunch of observations now, but not with complete detailed proofs. You can verify them. So you can also delete not just max, arbitrary element in order log n time. The only thing is that when it comes to delete max, I know it is in the root, but if I ask me, oh, delete 7, I don't ask me to search for 7, because that's a hard operation here. I'll tell you more about it later, but you have to tell me where the element is, right. So delete arbitrary element given by its location, then it's easy to do it in log n time. We just need, once that element is removed, you have to, take the largest element, put it there. No, take the last element in the array, put it in that element. You may have to go check with its parent or its children and do this trickling up or down kind of a thing. Here is a very useful, can be implemented in an array. Which means without explicit pointers. This is a very elegant feature of a heap. I will tell you what that means. So, by using level order traversal of the heap, what that means is, so for example, if I do a level order traversal of this heap, what I have, do you recall that you just visit level by level. So I'll have 25, 7, 15, 5, 4, 10, 9, 3, 11. So now suppose I store this entire thing in an array. Okay, so 25, 7, 15, 5, 4. I store this in an array. All I have done is I have read the values level by level and I have stored them here. You can just work with this array. I don't need these pointers at all. I'll tell you why. Okay. So now first of all, how are pointers useful? Pointers are useful to tell you who is the left child and right child, right? But turns out you can just use the indices to figure out left child and right child, because if this is the node 7, it is at location 2. You can verify because of the level order traversal and it's a complete binary tree that its children are at location 4 and 5. In general, any node in location I has children at locations 2i and 2i plus 1. I mean, maybe 2i plus 1 is not there, in which case it does not have the second child, it has only one child. Okay. Similarly, a node at location I has parent in location I by 2. Floor I by 2 because of the same reason. Okay. So, I just verified this as an exercise. Just please verify that if you have a complete binary tree and you take the nodes in level order, then the left child, right child, parent relationship can be inferred just by the index value, which means that this whole, because what are we looking at in this entire code of delete max? You need to know a node and its children, right? Once I know, I do a swap and then I look at its children and so on and so forth. Well, if the children of a node, if you are in location I, then I know your children are in location I plus 2i and 2i plus 1. So you know that you just go jump and figure that out in the array itself. So you don't need this explicit pointers, which is a very nice feature of a heap. Similarly, when I want to insert, what do I need to know? I need to know the parent value and the node value, right? Parent can be obtained by, if I am at this node, how do I insert? I add it to the end of the array and then look at its parent, which is sort of an, if n plus 1 by 2, floor n plus 1 by 2, and see whether there is a violation. If there is a violation, do a swap. After you've done the swap, compare the value of that node and its parent and see whether there is a violation, swap. So that means you can just maintain the whole thing in an array without explicit pointers and implement these two new operations, insert and delete max in logarithmic time, which is, so think of this as a heap order. It's neither sorted nor unsorted, but somewhere in between. It's not completely unsorted. There is some relationship because of this parent child value relationship. And if you read the nodes of a heap level by level and put it in an array, that array is in what is called a heap order. And if you maintain it heap order, you can do an insert, delete max, you delete the first element, take the last element, put it there, compare it with its children, you can go to 2i plus 1, do the swaps and all that. So you can perform both these operations in logarithmic time. Okay, and then a couple of more remarks. How much time does it take to set up, right? which is, let's call it as build heap. Okay, this is something which I did not really talk so much about. This is the pre-processing cost. That means somebody has given you the entire input in an array, arbitrary array. I want to transfer it into a heap. What do? One way to do it is, no, suppose this is the entire array, right? Your array A1 is a heap by itself because on one element, right? So insert A2 into the heap A1, right? You know how to insert an element into a heap. Now at the end of it, 1 and 2 have become a heap. In general, A1 to I is a heap. Now insert AI plus 1 into that heap. And then repeat, right? At the end of it, A1 to I plus 1 is a heap. Now insert the next. So keep inserting next element into an already built heap. That's all I'm saying. If you do that, at the end of it, you will have a heap on n elements, and the overall time, because we've seen that inserting an element into a heap on I elements will take log of I time, because that's, compare it with the parent and keep doing it. So overall it will be summation log of I going from, maybe in order 1 to n. So this is roughly order n log n. It's like a log n factorial, which is asymptotically order n log n. But there is another way, which I am not going to tell you. That means that, if you are given an array, view it as a complete binary tree, then you know that all the bottom elements, the elements at the leaf level, each one individually is a heap by itself. Okay. So now you go and make all the nodes at this level heap. Make subtrees at this level a heap, each one of them, okay, each subtree. After you have done with this, make subtree at each a heap, and then finally you can make the entire tree as a heap. I am not going to tell you all the details. Turns out it can be done in order n time. Okay, this is a non-trivial step, but all I want to tell you is that given an arbitrary array of n elements, you can convert it into a heap array in linear time. The algorithm is fairly simple. The analysis requires some careful calculation. So one algorithm is just keep inserting a new element into an already built heap. That's like an order n log n, but there is a way to do it in order n time. And finally, I want to just end with what is called a heap sort. Right? Heap can also be used to sort n elements. We didn't talk about how do I sort n elements, right? Suppose my input is some array of numbers or some elements from a totally ordered set, and goal is to sort them in increasing order, let's say, or non-decreasing order if there are repeated elements. So here is my algorithm. Build a heap, meaning convert the entire array into a heap order. So that's I already told you order n time or n log n time depending on what algorithm you use. More efficient algorithm you can build. So given this array, and this is converted into a heap ordered array. That means if you think of it as a level by level order, traversal of a tree, then that tree will be a complete binary tree with parent child relationship maintained. Now in this I will do a delete max. And put the element at the end. And recall what happens is that I will, the max is at the beginning, so this will be removed, some new element is going to come and I am going to put the max here. Now look at this heap, right, this is a heap on n minus 1 elements. Keep doing it. Right, I do a delete max, that will remove the next element and put it here, and then I look at the n minus 2 elements, do a delete max, put it here, at the end of it my array will get sorted. And how much time have I taken? Well, each delete max we already argued takes order log n time, and I am doing roughly order n or n minus 1 delete maxes. So this overall thing would be this is called heap sort, right? Build a heap and then keep doing delete. Once you do a delete max, automatically the heap operation ensures that you have a new heap on the remaining n minus 1 elements, right? And all that happens in logarithmic time. Now take the delete max, put it in the last location, build a new heap. Right? Automatically delete max operation cleans it up in a way that you have, after that the invariant is maintained that you have a new heap. Do a delete max, n times you do a delete max. In n times log n time, you can sort the elements. And notice, I want to make sure that it's an in place sorting algorithm. Means that everything happens in the array. In the input array with a constant number of extra space, some variables. One of the very few sorting algorithms where it's an n log n sorting algorithm and it does not use huge extra space. It uses space proportional to this, it's a constant number of extra variables, not space proportional to some function of the input size. Okay, good. So what did we see? We saw that this priority queue operations insert and delete max can be implemented by storing your elements in a complete binary tree with a parent child relationship, and you can support both these operations in logarithmic time, and heaps are very useful. One particular application of heaps is that you can sort an array of n numbers by building a heap and then doing delete max operations log n times. So that's an n log n sorting algorithm. It does not, and the whole heap operations can be performed in an array without explicit pointers or any additional space. Okay, I will stop this lecture